top of. Alright, so polynomials. So there are only three concepts that we need to look at. So the first one, it's really what we're doing in the HC course is based on estimating roots. Okay, everything that we do in the HC course is estimating roots when we don't have whole numbers root as the whole numbers solution for roots, or when we do long division, it doesn't provide us with the numbers that we need. Okay, so what we're going to look at is some approximation methods to be able to estimate the values of the roots. Okay, so first we're going to use our previous skills before we move on to the new skills on Wednesday. So the first one, find the exact roots. Okay, of that quadratic. Okay.
Negative 2 is a root.
Hey?
Negative 2 is a root.
Negative 2 is a root?
Yeah. What?
4, negative 24 plus 2, no. Not quite. Right, so we've got a quadratic. What's the first steps to finding the roots? What's the first technique we've learned to find the roots of a quadratic?
Oh, yeah.
No.
Quadratic formula, that one.
Quadratic formula. But before we go to quadratic formula, what will we do?
Just try it. Give it a thing. I don't know what it's called.
Factorise?
Factorise it.
Yep. Okay, if we can, we factorise two numbers multiplied to give the constant term, same two numbers add to give the middle term coefficient. Okay, so that looking like that's not existent at the moment, well, for integers anyway. Okay, so that's what the problem lies, that we usually base on integers. You could work it out using rational numbers. Okay, so you use some sort of fraction. For example, if you can brave to go through that and work it out, go for it. Okay. Otherwise, if we can't factorise, we have other techniques. Okay, so we have the quadratic formula. Alright, so negative b plus or minus square root of the discriminant. Okay, so this is memory of the formula. Okay, minus 6 plus or minus. So 6 minus 8. Okay, so we've got the problem because of the square root of 28. Okay, it's not a whole number if we go to give it square root of 28. Okay, however, I can write it as negative 6 plus or minus 2 root 7 over 2. Because 28 is 4 times 7, take the square root of 4 is 2. Okay, and we always have these things simplified just like your fractions. Okay. Okay, so they are real roots. They're not complex roots for extension 2, right? Because we got this discriminant is greater than 0, so the roots are real, right? There are two real roots. That means if we were to draw the sketch of the parabola, we know it's concave up because the coefficient of, so the leading term is positive, okay? And we've got two roots, okay? So it means somewhere we're cutting the x-axis twice, okay? So I know because I've got two roots, we've got an indefinite function there, so we've got part of it above, sorry, part of it below, and then the rest of the infinite amount of it above because it continues, of course. Okay? So, there's the exact solution. Alright, for the polynomial p of x equals that, we need to show part y that x take y1 factor. Okay, so I have to use my factor theorem. How do I do this again? Yeah, okay. So if the rule is if x take away a is a factor, then p of a is 0. Okay. So x take away 1 is a factor, so we need to show that p1 is 0. So 1 take away 7 plus 8 take away 2, which is 0, so that implies that x take away 1 is factor. Okay, so if it doesn't equal 0, whatever your value substitute into there, then it is not a factor. Okay, one of the benefits, one of the reasons, sorry, why we use find the factor is that we can find the rest of them, okay, by the process of long division. So, we need to find p of x as the product of factors. So what's the maximum number of roots I'm expecting? 3. Okay, so I've got one of them. Okay, so this can have one root. Okay, we can only have the one root. Right, we can have 2 roots. Or we have all 3 roots. Okay, it will depend on all the coefficients of each of those terms. So, a couple of ways we can do this. 2 different ways we can do it. What are they?
Long division.
Long division is one of them.
I'm guessing the rest.
Factor theorem.
Guessing the rest.
Factor theorem.
Guessing the rest.
Sounds fancy.
You're both correct, yes. Alright, so if I'm going to use the factor theorem, what's the approach I need to use?
Guessing.
You pick a factor
Of what? Of the constant. Okay, so I've done the proof in your prelim course. Okay, so we've got a factor of the constant term, can also be a factor of the polynomial itself. Okay, so I identify the factors of -2. Okay, both positive and negative equivalents. Okay, so 1, -1, 2, and -2. Okay, I can use those 4 and show hopefully that there are 3 factors, but it won't always work. Okay, because then you might have to go through long division anyway to get the other factors that are not introduced. Okay, so you can use a safe bet and use long division because that will get you your answers, or you have a guess and check method. Alright, let's see how well we remember long division. Alright. Right, so we need to make sure inside the quotient is every single power. Okay, if there's no power of x there, we need to include it and include a 0 as the coefficient. Okay, because what that will do is help with the consistency of the process. Right, so we need to identify the degree of the front and the degree what's inside the quotient.
Whoa.
Now we're ready. And if I've done this correctly, what should the remainder be? 0. If it's not 0, there's an error somewhere. Okay. Okay, so that means that will go to 0. That's what I need. Okay, so that means p of x is going to be that divisor multiplied by the quotient, add the remainder. In this case, we're not adding anything there. So we're asked to find the product of its factors. Okay, so that is the factor here. Alright, but we don't have the full list of factors just yet. Alright, so we need the factors of this quadratic here. So two numbers multiplied to give 2, same two numbers add to give -6.
3 plus or minus 7. -3 plus or minus 3 7.
Ooh, we'll see. Alright, so x is going...
This is a negative 0.
It'll be 3 plus or minus
4 times 1 times 2. Oh, I guess, hang on. We are... That's really part 3, isn't it? Product of its factors, yes, sorry. That's correct there. That's done. Okay, because we can't factorise that anymore. We had to use the quadratic to get the solution. Okay, so we can't actually factorise this anymore. So, obviously tell I'm a bit rusty from my weekend adventure. Wow. Alright. So, we need to identify whether we can factorise this. If we can't factorise this, then that is in its full factored form. Okay, so really what I've started to do is find the roots. Okay, which is that part there. Okay, find the roots. So the roots are not in integer form. All of them anyway. Okay, so we've got 3 plus or minus root 7. Okay, which would be irrational numbers because root 7 is an irrational number. Okay, and we also have the root out the front here. The exact way 1 equals 0. So therefore, roots are 1, 3 plus or minus root 7. Okay, so it's good to get the approximation so that if we were to sketch the polynomial, okay, we know approximately where the roots are going to be. Alright, so that's algebraic that we have covered before. Yep. In there, so what we are going to look at this topic is some techniques to approximate your roots. Okay, any questions there?